when I do AI, I do it in Clickhouse. So let's do some experiments. What can we do? Don't worry, I will not create new AI models. I will not train AI models inside Clickhouse. I will do inference. And I will apply Clickhouse for semantic search. And let me introduce the way how we can do it. We can use user-defined functions in Clickhouse. And there are different kinds of user-defined functions. There are regular functions. There are user-defined table functions. You can use it like this. Select from executable, specify a script name that should be located in a specific directory, specify a subquery that will get some data and pipe it into the standard input of the script, and this script will return data back to the standard output. There are user-defined dictionary sources. You can create a dictionary with the executable engine and also specify a script. And this script will take some keys and return some values, and you can use it as a dictionary. For regular functions, there are also different kinds of them. There are SQL user-defined functions that you can create like this. Using create function query, you specify the name of this function, and you specify it as a lambda expression. For example, this function will calculate the number of white space characters in the string. It can only reuse other functions, so these functions could be created as a simple expressions. And if you use these functions as usual, and they work. It is quite limited. So there are no recursion, no loops, no complex logic, but they are lightweight and easy to use. The problem, I cannot use these functions for AI, and I want to do some AI. It sounds trendy. It sounds nice. So another type of user-defined functions are executable user-defined functions. So for this, I create a script. I put this script into specific directory, name it user scripts. I make this script executable. And the same function can look as simple as this. It will count the number of space characters in the string. This script will receive data to standard input. Every tuple of arguments as on a line. By default, it will use tab-separated format, and it will print the result also in a tab-separated format. I have to provide the configuration. A specification of this function, it can be in a specific configuration file that will be loaded at runtime, and it looks like this. I specify the type. Here the type is executable, the name of the function, the format that will be used for input and output, the command to run, the return type, and the types of arguments. And it works. So the script will be invoked for every block of data. It will be serialized, written to standard input. The block of returned values will be read from the standard output, deserialized. So it is pretty primitive. But still, the script will not be invoked for every record. It will be invoked for every block. This invocation will be parallelized. So if your query is processing data by multiple threads, it will run multiple copies of this script in parallel. And it can be configured and reconfigured in runtime without system restart. So let's take a look about the performance of these functions. The first one is SQL user-defined function. And it runs with a speed of 1.30 billion records per second. Is it fast? Probably. Probably it is at least over a billion. The second function with a Python script runs only with the speed 40 million records per second. If I just not show you this, maybe you will say that 40 million records per second is quite good. But you have to know how ClickHouse, what ClickHouse is capable of doing, and compared to typical ClickHouse queries, it is not fast. But the upside, it allows any programming languages. It runs in isolated process. It is slower due to data marshalling. And also we can ask a question. We have written this code in Python. Maybe it is slow because Python is a slow programming language. So why not to use Rust? Why not to use C++ to do the same? But maybe this approach will be suitable for our purpose, for machine learning and AI. Actually, we can do a few optimizations. The first optimization is pooling. We configured this script with the type executable. And this script will be run entirely a new invocation of the process, a new instance for every block of data. Like 65K of records will be processed by a script. The script will finish, then it will run again. And every time it will wait for the script to finish. And another option is the type executable pool. What it will do? It will launch the script and keep it running, keep it active. It will just continue piping new records to the script. And the script will have to output the result to be consumed as soon as they are ready. So there will be no initialization cost. You will be able to specify the size of the pool, like 16 concurrent processes, 100 concurrent processes, whatever you need. So let's compare the performance. To the left, it is the executable type, and it is absolutely simple as it could be. 40 million records per second. To the right, it is the executable pool. And the only difference, we have to flash the output to avoid buffering. Otherwise, the other end of the pipe will just wait for the records to appear, and it could wait for a long time. And it is 10 times faster. So maybe Python is not as slow as we used to think, but it is still less than 1 billion. Let's take a look at another optimization. It is named chunking. For executable pool type of the script, there is the default option. And the default option, as we saw, it was just 400 million records per second. But you can change and specify the option send chunk header equals to 1 in the specification of the user-defined function. Then ClickHouse will serialize data in a slightly different way. First, it will write the chunk size as a number to standard input. Then it will serialize that number of records. So we have to read the chunk size and then read that number of records in the loop. And the only difference, here we flash data every record, and here we flash data every chunk. And the difference is 1.5 times performance improvement. That's actually pretty good. OK, so how to achieve the maximum performance for executable user-defined functions? Pooling, chunking. Also, we can change the serialization format. It was tab separated, but we can use Apache Arrow. It is accessible from Python. It is easy to use. You can also use it from Rust, raw binary format, or even native format. Whatever you will find faster or convenient to you, or you don't have to use Python. Maybe you should write it in Rust. At least you will be fashionable, you will be trendy. But there is one good news. AI models are really slow. They cannot process billions of records per second. They cannot even process billions of tokens per second. So my question to you, how many tokens per second a typical LLM can process? 100, okay. I'm staying in AI town. Everyone should know these numbers. Yeah, probably 100 or 1,000. It depends on the service. It depends on the hardware, how you run it. But yes, something in order of hundreds to thousands. So we don't have to use all these optimizations. OK, what I actually want to do. I want to run machine learning and AI models. I don't know what to say better. If I would like to keep myself old-fashioned, classy, I would say machine learning. If I want to be trendy, I would say AI. I do AI. But OK, let's do semantic search with vector embeddings. And sorry for telling it one more time. Everyone in this audience should know what is semantic search. So with classic text search, like in whatever, Lucene, Apache Solr, you find documents by search terms by comparing the words, the actual text of these terms. With semantic search, you compare not the actual text, you compare the meaning of this text. And to do it, you first transform everything, whatever. It doesn't have to be text. It could be images. It could be music, video records. You convert it to some vector of like thousands of numbers. And you do it in a way that similar vectors by certain metric will correspond to similar meaning, similar semantics of these objects. And you can do it with OpenAI, Anthropic, with local models, whatever. And these embeddings are typically pretty big. Typical numbers like 384 or 1538. And you have to calculate the distance between these vectors, so it will correspond to the similarity of the objects. And let's create a function that will look like this. I want a function named embedding. And it will return a vector of a certain number of dimensions, a vector of floating point numbers. And we will use a data set, all comments from Hacker News. It is pretty big. It was 30 million text comments when I created this presentation. Now it is about 40 million. But the actual volume of the text is pretty small. When I put everything into Clickhouse, it is just 7 gigabytes. 7 gigabytes will fit, I wanted to say on a flash drive, but it will be, flash drive will fit 100 times more. So let's say, no, I should not say DVD because I'm not that old-fashioned. But the actual amount of data is really small if you put it into Clickhouse. And we want to generate vector embeddings for every title and a comment. So let me see the table, 28 million records, 7 gigabytes. And if we do a brute force text search, it actually works. And it works. Let me also check how I will do a brute force text search with the like expression. Clickhouse is fast, and it works in half a second on some laptop, probably. So now let's start generating embeddings with transformer models. I don't have even to use GPT. I can use something named mini-LM-L6v2. And it is really outdated model. It is primitive. And the script will look like this. Here I load and create the model. And for every record from standard input, I will take a batch, take an array of records and run the model on this array. And then I will just print the output in a JSON format. That's it. And the configuration, I will use a pool of size just 2. I will explain why, and it will be executable pool, and the function will be named embed. And the format is tab separated. I used JSON here, but actually it works as tab separated as well. It will just output an array. The argument is string. The return type is array of floating point numbers. I also specified some timeouts just in case. It makes sense. And the usage to test this script, so I used chunking, send chunk header equals to true. To test the script, I will put the chunk size, the example record, a few new lines, and just run this. I don't know why I need sudo. Probably, it is just to run it from Clickhouse. Let's take a look. I will test this function inside Clickhouse. Embed of hello world. It works, and it took only 8 milliseconds. Now, if I try goodbye world, it also works. No surprise here. Now, let's take a random data sample from my table and what I'm trying to do here. And we will embed the title and the text, just concatenation of them with white space. No, with new line. I want to calculate embeddings. And it is also fast, 14 milliseconds, but we did it for just 10 records. Now, what I'm going to do next, I'm going to check how fast or slow it is if I run it for every record. And 1,000 records per second. No, 50,000. No, it is slower. It becomes slower, 20,000 records per second. Why it is so slow? 17,000 records per second. The vector size is 384 floating point numbers. OK, it was just 10,000 records per second. But the truth is that actually it is the performance of this language model. It works in this way. First, it showed better performance because it started to pipe blocks for processing. But the actual sustained performance is just 10,000 records per second. But let's take a look, some comparison, what the performance on a different hardware will be. If we take a pretty large server, previous generation, but still really large on AWS, it will be just 265 records per second. Oops. It is unbelievably slow. If we take a GPU that is not a gaming GPU, not a GPU for language models, it is GPU that I bought because I don't play games. I don't really need a GPU. It is just a couple of bucks, and it is faster than the one of the most powerful machines on AWS. But if I take a GPU-capable machine in AWS and use it properly, and it is also a very primitive machine, one of the previous generation from many years ago, it is more than, not more, about 8 or 9 times faster than CPU. If I use just a decent, but not actually good, just a decent GPU, it will be even faster. And on a proper GPU, it should be even faster, but I did not try it. OK, let's take a look what will happen. I created a table, and I put all embeddings there. Here is the column named vector of type array of float32. And I'm trying to calculate embeddings, and I fill this table with a simple insert select query. So I create a table Hacker News embeddings and put everything plus additional column with my embedding. And after just a few hours, all 30 million records were processed. I used a few tricks. First of all, I lowered the block size. What is the default block size in Clickhouse? Do you know? What?
A bit over 1 million.
No. The default block size for processing data.
8,000.
This is almost correct answer, but not quite. Who will tell the truth?
8128.
What?
8128.
No. It is the default granular size in Clickhouse. The default block size for data processing is 65,000. Okay. And there is a reason for that, but I will not ask what is the reason for that because I don't want to be disappointed. So I lowered the block size quite a bit just because we will have to process these large arrays. And these large arrays will take a lot of memory. They will not fit in the CPU cache. So definitely it makes sense to lower this internal batch size of Clickhouse query engine, which is named max block size. Actually, GPU might not benefit from that large batches, but you have to experiment. I used executable pool type of function. I used chunking, and I used the process pool size of 2, something between 2 and 4. Because the reason is that when I collect a batch of text and pipe it into the model in Python, I used PyTorch, and it will use internal parallelism. And with this internal parallelism, I don't have to parallelize externally. So the pool size of 2 is actually enough. And moreover, if I use a larger pool, maybe I will run out of GPU memory. Let's take a look. So another question, how to use these vectors, how to compare them. And to compare the vectors, we have a set of distance functions in Clickhouse. They are available out of the box, like L2 distance. Actually, for the most of the models, you will use cosine distance or dot product. But just in case, we also have LP distance, L1 distance. Every distance you want to use, it exists in Clickhouse. And here I will use order by L2 squared distance between embedded vector and some target vector. And the target vector I will calculate on the fly like this. And I will check the top 10, the most similar results, similar to the phrase Clickhouse is fast. Okay, here is our target vector, here is the distance, and we will order by distance limit 10. And how fast it will be? 0.6 seconds. So the result is, how does it compare to Clickhouse? Sorry, this is not obvious, but what is Clickhouse? Not to mention Clickhouse. Can confirm Clickhouse is generally faster across most typical workloads. If you want cost-efficient high performance, Clickhouse is hard to beat. I like these results. So apparently it works correctly. Clickhouse is another favorite. Now let's do something like we will exclude results containing the Clickhouse substring. So we will again look at the most similar results, but without obvious matches. Not like Clickhouse and not like. So sell house fast. Chinese click farm. Wow, Clickhouse is right up there. Now I'm in doubt. Probably it does not work. Not work. It is AI after all. It has to have a little bit of creativity. Okay, now let's try to include Clickhouse, Redshift, and what it will be. Redshift is based on Paraxel. We used. Okay, Surf Analytics, Redshift counter. So I'm still thinking, is it correct, or what if we'll compare with, Hadoop is slow. And how the results will, and now we will include results with the Clickhouse substring. Let's take a look. If you're disappointed with the speed and complexity of your Hadoop cluster, and especially if trying to crack it, you should give Clickhouse a spin. I like these results, so it works. But now let's do some more serious validation. We will probably compare the performance here, how fast it could be. And if we try to calculate embeddings on the fly, it is just like a few thousand of records. And we can monitor the GPU usage at the same time with the command nvtop if you use NVIDIA GPU. And it shows the memory utilization, the overall GPU utilizations. And it looks like the GPU is utilized, and 2000.5 records is the maximum we can get on this poor GPU. Okay, there is enough memory, and GPU is utilized. What optimizations can we make? The first optimization is we don't have to store vectors of floating point numbers with full precision. We used float 32, so 4 bytes for every vector. And it will take 1.5 kilobytes for every record in memory. But we can use half precision floating point data type, and actually not the standard half precision, but bfloat 16. Bfloat means brain float. The name came out from Google, but actually it was used even before. And the trick is that a single precision floating point data type has the sign, exponent, and everything else, name it mantissa, and we can just cut it in half, and we will have the same number of bits for exponent. So the range will be the same, but the precision will be lower. We can convert from float 32 to bfloat 16 like this. But actually don't look at this function, because good news, in the latest Clickhouse version, 24.11, we have a built-in bfloat 16 data type. So you just write array of bfloat 16, and you can insert floating point numbers as usual, and they will be automatically converted to a half precision data type. And it is less precise, but the results should be about the same. Let's take a look. Oh, it is faster, 0.3 seconds. And the table with float 32 has 44 gigabytes in uncompressed data, and the table with bfloat 16 should have just half of that. And the query runs 0.3 seconds. It is faster. It is faster. And the results are exactly the same. You should give Clickhouse a spin. Now let's compare in more detail. Clickhouse is a better fit for some tasks. Clickhouse hugely outperforms on query patterns. Nice. Okay, another optimization is pre-filtering. We don't have to sort the data by distances and compare distances of 30 millions of records. We can cut off distance by some number and just then order by the distance. We can also lower the index granularity of the table because table records are quite large. And actually what we did was brute force search. What it really did, it took all the records, go through all the records, compare all the vectors, calculate distances, sort these distances, and take top 10 results, and everything in 0.3 seconds. Can we make it faster? Yes. There are vector indexes, and there are many types of vector indexes, like HNSW, like NOI, and there are many libraries and many databases that contain these indexes out of the box. Currently, Clickhouse does not have any production-ready vector indexes, but I want to build my own directly in Clickhouse using the available tools. And we will use a simple technique, name it random projections or random space partitions. The idea is we have our vector space, it is multidimensional, and we have many points in this vector space, and we want to split it, like split it into two halves. So half of the vectors will be in one, half will be in another, like this. And we just take a pair of random points, took a middle point, and make a hyperplane that is normal to the line between these points. So it will ideally separate these two random points. And then we will figure out on which part every point is relative to this hyperplane. It will split the space. And then we will split the space again and again. And every time we will get one bit of information. And we get as many bits as we want. And it looks like this. I made this picture, and I like this picture so much. I want to print it, put it in a frame, put it somewhere in my house. It is so beautiful. It is a multidimensional space with a lot of hyperplanes splitting this multidimensional space. I can do it with SQL. It is not as cool as DoorDash showed me with Clickhouse local, but still quite a simple query. We will create a table with hyperplanes that will split our space. Each record will contain a normal defining a hyperplane and offset of this hyperplane. And we will calculate these hyperplanes by taking 256 random pairs of points. Here is one point, here is another point, and we will calculate the vector between these points, and we will also calculate the offset and insert it into our table with hyperplanes. We also take every data point and calculate a scalar product with our normal minus offset, and it will give us one bit, and we will put these bits into bit mask by shifting them and get all of this together into a single bit mask inside uint 128. So it will be our vector index. So to calculate the similarity, we will use a Hamming distance. How many bits are different in the same positions? And compared to the original distance, calculation of this distance is much faster because we have to compare less amount of data. But actually, I tried it and get almost nonsense results because the relevance was not there. It was much worse than with the original distance. But actually, I can still use this index in a very interesting way. So the approximate distance is not suitable to get top 10 or top n results. But I can get some threshold on the approximate distance, filter with this threshold, and then I will calculate the real distance. Here is the real distance. So I will filter by the approximate distance and order by the real distance. And probably it will work. Let's take a look. Will it work? What do you think? At least I made my presentation not for nothing, so it should work. The column with bits is much smaller than the original vector, 100 times smaller. And let's do it. Let's run it and see how it works. First, without filtering, the exact match. And the exact match took 1 second. Now, let's do the same with filtering by the approximate distance. The first column is the approximate distance, and we see that the threshold should be around 40. And here we have 50, just in case. OK, and is it fast? No, something happened. It is not fast. So what mistake did I make? Let's try 40. Oh, it is faster, 0.9, but still not enough. The results look very relevant. How does it compare to Clickhouse? Sorry, but yeah, the same results. So let's try to lower the threshold again. 30. The same results, and it is 2 times faster, 0.4 seconds. Now, what if I will select even less, 25? Oh, it is fast, but kind of, it degraded. Kind of relevant, but not quite. And with 20, oops, almost no results, but it still works. OK, here was our experiment. We used some tricks, like lowered index granularity. We did some optimization for insert. We used our bit mask as the order by key to speed up searching. And this is basically it. And as a demo, we made this interesting application to search for dogs or cats. And the proof is I put a dog, and it finds dogs. So it works. OK, takeaways. There are specialized vector databases. There are a lot of specialized vector databases, but who cares? I don't. Clickhouse is always the best. In Clickhouse, you can run your models, whatever models, as user-defined functions. It has support for vector data types, vector operations. It is not limited by memory. It is not limited by a single machine. It scales well. You can do pre-filtering, post-filtering, precise, approximate search. You can do analytics on the results. You can combine analytics with search. So that's it. Thank you.
Hi, thank you for that talk. Are there any opportunities to integrate something like one of those vector search algorithms that aren't linear but logical?
Yeah, we decided to implement HNSW, and currently it is in beta. We announced its availability just a few days ago at AWS reInvent. It is already available for experiments for your feedback. It will soon be also available in Clickhouse Cloud. And actually, if you are already a customer, you can subscribe to the fast release channel, and you will have a chance to get this feature the first.
Fantastic. Thank you.
What is the impact of reducing the index granularity for large rows and improving performance?
When you filter by preware or filter by primary key, the minimum unit of filtering is a granular. And if you have large records, every granular can be also large. So every vector is 2 kilobytes. If you multiply by 10,000, it will be 20 megabytes. And these vectors also not compress much. They are almost random. So the solution is just to make granulars smaller. And you do it by lowering the index granularity. And also the minimum amount of data for reading is also a granular. So if you read 20 megabytes using, for example, 64 threads, it will be more than 1 gigabyte. And more than 1 gigabyte will have to, it will be not good for the memory subsystem of the machine, memory bandwidth. So it makes sense to lower it, and in practice it is faster.
So for user-defined functions in Clickhouse Cloud, is there a way to get Python ones working?
Yeah, we did not announce the general availability of user-defined functions, but the secret is that a few customers already use them. They just requested them through support, and we installed these user-defined functions. We had to take specific security measures, so these Python scripts will run in isolation.
Right.
It's actually a very interesting technical problem that we had to solve. So if you are interested, just create a ticket and we will do it.
All right, amazing. Yeah, thank you.